talking about chapter 3 now. Chapter 3, we're looking at observations. Observations, typically when you do these observations, you want to be as exacting as possible. And so we like to measure things. And so observations are just measurements. And the more what we call quantitative, the better. And quantitative is different. We have two kind of levels that describe measurements or observations. We have qualitative. Qualitative would just be rough observations or rough measurements. For example, the color, that's a green color. Whereas if you were to do that quantitatively, you'd use like something that measures the color. Like, for example, each color has a frequency or wavelength associated with it, and so you could get different shades of green or different shades of blue, whichever. And so that would be quantitative. So quantitative, we're much more exacting in the measurement. But when I say exacting, it doesn't mean that it's exact. It's getting closer to what we'd say is more accurate or more precise number. Because one thing all measurements contain is something called uncertainty. So let's say all measurements contain uncertainty. So, if you measure the length of this table, is, what would you say? 12 feet or something? That would be pretty qualitative. But, if I took the meter stick and then actually measured this as exacting as possible. So, let's see, 2. And so I came out to, let's say, 1.2 meters. Is that exact? No, it's not exact. But it's more exacting. It's more what we call precise, more accurate. And so when we're thinking about uncertainty at this point, we're going to look at two types of uncertainty that we have. We have something called precision and accuracy. Consider in terms of that. And so something that's more quantitative will have a higher degree of precision and a higher degree of accuracy than something that's very qualitative in terms of measurement. And if we have a higher degree of precision and a higher degree of accuracy, then we have less uncertainty in that particular measurement. So let's take a look at some measurements right now, and then see what we can do. So as far as measurements go, we can have something like this, 0.5 kilograms, kg, 0.5 kilograms. If I have 0.5 kilograms, there is some uncertainty in that, because if this were a measurement, one thing I could say is I could say exactly 0.5 kilograms. If I said exactly 0.5 kilograms, then there's no uncertainty in this. It's exactly 0.5 kilograms. If there's no uncertainty, then how do we show that? Well, there are different ways we could show that. One way is we could just leave it like this and write the word exactly. Here. Another way we could show this is we could have a 0.5 and then an infinite number of zeros. Well, we can't show that because it'd be pretty hard to write an infinite number of zeros. And so what we do is we have something called significant figures to help us with this. And significant figures for exact numbers are hard to represent. We just know if it's an exact number, then there are going to be an infinite number of digits here. And so that would be just abbreviate SF for exact numbers. Now we can contrast that with this. And so if it were a measurement, you know, let's say we're measuring something and it weighs 0.5 kilograms. So I'll take an object like this stapler, and the stapler weighs 0.5 kilograms. Would you say that's exact? I mean, I know that it's exactly 0.5 kilograms. No more, no less, exactly 0.5 kilograms. Would you think that's possible? No, this is going to be approximately 0.5 kilograms, right? And so what we can say is that, okay, if it's a measurement, then it's going to be 0.5 kilograms. Usually when we're doing exact, these are usually by definition. And so I'm defining that as exactly 0.5 kilograms. But in a measurement, in a typical measurement, we show it in different ways. So for example, in this one, do you know how many sig figs? You might have encountered sig figs in the past, but how many significant figures in this number? Would you say 2 significant figures in this number? Or 1? Or maybe you haven't encountered. I mean, how many people have never done sig figs before? A couple of you. Okay, the way we do this is this. There's a certain set of rules. These significant figures rules. But you know, with rules, you have to keep something in mind. You know, are rules more rigorous, more exacting than laws, or are laws more exacting and more rigorous than rules?
Laws more exacting and rigorous.
Yeah, laws are more exacting and rigorous. For example, there's something called the laws of thermodynamics, and the laws of thermodynamics, they have this one law which pretty much says you cannot have a perpetual motion machine. So for example, if you have a wristwatch, you know, you'll have to wind it up or put a battery in there. You know, eventually it's going to stop. Nobody's invented a wristwatch that can just keep going on forever, like a perpetual motion machine. Even the ones that you don't wind up and the ones that you don't put a battery in, they rely on
Your movement of your wrist.
yeah, they rely on movement, and so that movement converts the kinetic energy of the watch into potential energy, and the potential energy is stored so they can operate the wristwatch. You know. Nowadays, I was at the like I said, the CS show, but there's a lot of talk. You know, people want to put these things in clothing, things that convert mechanical energy into electrical energy, so they can charge the battery or power their electronic devices just by walking. So they can always have that. But anyway, so people have been trying, and people have claimed to have made perpetual motion machines. You know, these things that just keep on going without any input. But nobody's ever. All those claims have been disproven. There's no such thing. And so this is the laws of thermodynamics, and people have been trying to find violations of the laws of thermodynamics for hundreds of years, but have not been successful. There are some laws that do have exceptions. For example, the law of conservation of mass. You know, the only reason they found the exception is because of nuclear reactions. If it wasn't for nuclear reactions, they would have never noticed the slight difference in mass. And so they had to modify the law of conservation of mass, call it the law of conservation of mass and what?
Energy.
And energy. So if you combine those, then we're okay. For us, we don't really have to worry about it because we really aren't doing any nuclear reactions in this class. So law of conservation of mass, pretty much we can just use standalone because the mass, when you weigh before and after, it's the same. And the same thing with law of conservation of energy. Look at the energy before and after, it's the same. Essentially. But laws are pretty rigorous. Rules, there can be a lot more exceptions. These are significant rules, significant figures rules. And so you have to, you have to be aware that there are going to be more exceptions. Sig figs don't work out perfectly for what they're intended to do. Now, what are sig figs intended to do? Sig figs are intended to give you some idea of the uncertainty in that particular measurement. Now, how does sig figs give you an idea of the uncertainty? They talk about the precision of the measurement. The precision is, how precise, when I think about precision, I think about a range of values. So if I have 0.5, kilograms, okay, the stapler weighs about 0.5 kilograms, well, then I don't think that's exact because that's a measurement. Whenever we have a measurement, it's not exact. There's uncertainty associated with it. If it were defined, okay, I'm going to define the mass of this stapler as 1 stapler unit, and that would be exact because, yeah, this is 1 stapler unit mass. That would be a definition. And so when we have something like this, then the range of this would vary from anywhere from maybe 0.46 kilograms, because 0.46, if you were to round this, and drop the 6, we'd have to round this to 5. So if that stapler weighed 0.46, so that's 0.5, all the way up to 0.54 kilograms. And so when I see a measurement like this, I'm typically thinking of this degree of uncertainty. The stapler can weigh anywhere from 0.46 to 0.54 kilograms and still be called 0.5 kilograms. And so this range is kind of the range of precision. We would represent that range as something like this: 0.5 plus or minus 0. Then we take this, the smallest unit is 10, so it goes 0.1, 0.2, 0.3, 0.4, etc., 0.5. And so we take half of the smallest unit, which would be 0.1, and half of that would be 0.05. So typically we'd set this as the range here, 0.5 plus or minus 0.05 kilograms. And so when I see something like this, this is what I think. Now, what we do is we call this, in terms of sig figs, we call this 1 sig fig, 1 significant figure. The reason we call it 1 significant figure is because the zero is what we call a placeholder. And what the zero is, for example, if we were to rewrite this number in scientific notation, how would you write this number in scientific notation? It would be, we'd call it 5 times 10 to the negative 1. So if we make this number bigger, so we went from 0.5 to 5, we got to make the exponent smaller. So this grows, this shrinks, is the way I remember it. And so this would be 5 times 10 to the minus 1 kilograms. Now, is it important to have that 0? Should I call it 0.5 times 10 to the minus 1 kilograms? No. And so that 0 is not significant. We call it insignificant. And therefore, this only has 1 significant figure. Okay. And so this would be an example of a measurement. Now, let's say I weighed this, on a better balance. The balances are used to weigh, it's like a scale. So I'm using a more expensive, fancier scale. A fancier, more expensive scale could have a higher degree of precision. A higher degree of precision means it can narrow down that weight to a smaller range. And so something that, like a scale, I'll just use a more expensive scale, and the more expensive scale might give me a mass of 0.50 kilograms. Now, a lot of people will say, 0.5 and 0.50 are the same mass. They aren't the same mass, because when chemists think about these measurements, they're always thinking in terms of uncertainty. How much uncertainty do I have? What is the range in values? Because what would the range, the expected range for this be in terms of the precision? It might be anywhere from This one might be anywhere from 0.495 because 0.495, if we drop the 5, it would round to 0.50. Everybody's familiar with rounding? I think in math, they cover that pretty well. So it could be 0.495 all the way up to 0.504, because if we go to 0.505 and we drop the 5, we'd have to round that up to 1, not 50. And so this would be the expected range in terms of kilograms here. Now when you look at this range is a much tighter range. It's a much narrower range. So when we're looking at this is going to be 0.50 plus or minus. Now the smallest unit here is going to be 0.01. So this will go from 0.50 to 0.51 to 0.52. And so if the smallest unit is 0.01, then we'll take half of that. So we'll go 0.005. And so this would be 0.50 plus or minus 0.005 kilograms, approximately. You know, not exactly, because this is not exact. I mean, if we did plus 0.5, that would give us 505. So we can only go plus 0.04, but we can go minus 0.005 because of rounding rules. But you know, it's approximately this. Sig figs. Remember, sig figs are not highly rigorous in that sense. So we got a little play there in how we do it. Now take a look at the uncertainty here. When you look at the degree of uncertainty here, it's much smaller than the degree of uncertainty here. You see that? And so what we say is this is a much higher precision than this, even though the numbers are the same. You know, the uncertainty in that is a lot less. The way we represent that is by the number of, the precision is represented by the number of what we call significant figures. And so here we have one sig fig, which isn't going to give us great precision, but here we have two sig figs, right? Two sig figs. Like this. That's good. So, for example, you know, if you were to, let's say, if you were to buy a kilogram of gold from me, right, or maybe make that a half a kilogram, you're going to buy a half a kilogram of gold from me, right? And I say, okay, I'm going to sell you 0.5 kilograms worth of gold. But I'm going to be very careful, because when I give you that 0.5 kilograms of gold, I'm going to use a very exacting balance. I'm going to actually just weigh out 0.46. See, I weigh out 0.46, then you're going to come out short, right? You're not going to get as much gold as you thought you were going to get, but hey, it's 0.5. Isn't 0.5 0.5 because 0.46 rounds to 0.5? Isn't it the same thing? It is, because, I mean, that's 0.5. So if you're going to go out and buy some gold, then you probably want to use a high precision balance to make sure there's no funny rounding business going on, right? Otherwise, you're going to lose out. Yeah, some people, they don't, you know, they don't care, maybe, or maybe they do care, you know. I think everybody cares. And so to a chemist, these would be different. If you're buying gold, of course these are different, you know. You probably, if you're buying gold, you probably want the most precise balance you can get, you know. For example, this is, actually we can get even more precise. We can go to, let's see, what can we go to this, 500. We can go to this, the balances. We have, not in this class, but in the next class, Chem 1A, we have balances. I can go to that. And so if you weigh out the gold to using this, then you know, well, you might be short like a tenth of, or let's see, half a tenth of a milligram. Like you might be short a milligram, right? You might be short a milligram. But you know, here you're going to be short a lot more. You would be short 40 grams. If I gave you 0.46 kilograms instead of 0.5, you're short 40 grams. A gram of gold is like 2,000 something bucks. That's a lot to be short. All right, so we use sig figs to give us an idea. I'm going to talk more about precision and accuracy as we go along, but we want to right now look at sig figs and precision. That's what we're going to focus on. We'll talk about accuracy in a little bit. But what we're going to do is we're going to look, well, if I have 0.5 kilograms, how many pounds is that? 0.5 kilograms is equal to how many pounds? Well, do you know how many pounds are in a kilogram, or how many kilograms are in a pound? 2.2, right? 2.2 pounds in a kilogram. And so one thing I could do is I could just do this, I could just say, okay, one example of doing this is the setup we do. And this is going to be an example of dimensional analysis. Dimensional analysis is how we solve a lot of problems in chemistry. Not all of them, but most of them are going to be solved using dimensional analysis. Dimensions are the units, like kilogram would be a dimension, grams, pounds, all these are dimensions. So dimensional analysis, what we do is like this. We have kilograms here, we got to relate kilograms to some other dimension. And one dimension that we could relate it to is like this. We could say that there are 2 pounds in 1 kilogram, right? And so you could say, okay, you know what? If you're going to buy 0.5 kilograms of gold from me, I'm just going to give you 1 pound of gold, because there are 2 pounds in a kilogram, right? And so it's 0.5, so that's just going to come out. The way dimensional analysis works is kilograms cancel each other, and we end up with 1 pound. So I just owe you 1 pound. If you buy 1 kilogram of gold from me, I just owe you 1 pound. Is that good? That's good, isn't it? Because 1 pound is the same thing as half a kilogram, right? But you might not be so happy. Why? You might not be so happy because I just made what we call an error. Some people would say, there's no error, that's right. But some people would say, there's an error. Like me, I would say, there's an error. You know what I call that error? I call that error a round off or sig fig error, a rounding error. Because, I just shortchanged you. If you bought a half a kilogram of gold and I gave you 1 pound, I just shortchanged you 10%. You lost 10% of your gold. How? Because of I just rounded this from, it's actually not 2 pounds, it's actually 2.2.
And even then, it's still.
But is that exact? Is it exactly 2.2 pounds in a, no, it's not. It's not. And so if I gave you 2.2 pounds for every kilogram, you know what? I'm shortchanging you. If you ship by UPS, UPS doesn't use 2 pounds per kilogram. UPS doesn't use 2.2 either. They don't use 2.2 because it's not accurate enough. It's not precise enough. In fact, they're going to be using more because this is not by definition. This is actually a measurement. Somebody measured how many pounds are in a kilogram. That's it. And when you take a measurement, there's uncertainty. And so we have different ways we can represent this. This is called 1 sig fig. Um, 2.2 would be 2 sig fig. But, okay, so how much would you have been short? And so if we do 0.5, you would have been short 10%, because really you would have been owed 1.1 pounds. And so I go, oops, my mistake. Actually, yeah, you're right. You should have been given 1.1 pounds, not 1 pound, right? But do you know I'm shortchanging you a little bit more? I'm shortchanging you a little bit more. It could have worked in the reverse direction, Like if you were the seller of the gold, it could have worked in the reverse direction depending on how you did this. But this is 2.2. Actually, how many pounds are there in a kilogram? It's not exact. That's something that's measured. And let's take a look. I don't have it memorized. You know what? I haven't memorized the 3 sig figs. The 3 sig figs is 2.20 pounds in 1 kilogram. So for every kilogram, I have 2.20 pounds. But if I'm buying gold, that's not good enough. Because, hey, it seems like pretty good. This is 3 sig figs. 3 sig figs, hey, I get the same answer. And the way it works is something like this. This would be 1 point. Actually, I shouldn't do this because we have a problem here. We have a problem about how I define 0.5 kilograms. And so this is what we call either 1 sig fig or exact. It's 1 sig fig if I'm talking, hey, it's anywhere from 0.46 to 0.54 kilograms. I want anything between 0.46 and 0.54. That's 1 sig fig. It's exact, meaning, I want to buy exactly 0.5 kilograms. I want 0.5 kilograms. I'm going to pay for 0.5 kilograms of gold. Right? So how many pounds should that be? Should it be 1 pound? No. Should it be 1.1 pounds? Getting better. In fact, this is the same. If I call this exact, because let's say for the purpose of this, I have exactly 0.5. I want exactly 0.5. Then I need to weigh it out. Well, how much should I weigh out? Should I weigh out 1 pound? No. Should I weigh out 1.1 pounds? No. In fact, I should weigh out, because 1.1 pounds could be anywhere from what's a range on something like that? If I have 1.1 pounds, it could be anywhere from 1.05 to 1.14 pounds. If I go in and buy 0.5 kilograms, the guy said, okay, I'm going to weigh out 1 pound. Well, when they weigh out 1 pound, that's just a 1 sig fig. If they weigh out that to 1 sig fig, that could be anywhere from 0.95 to 1.4 pounds. Well, it would be great if you got 1.4 pounds, right? But it would really be bad if you only got 0.95, and they say 0.95, well, that rounds to 1. Therefore, you got your 1 pound. And so, again, the answer here has 1 sig fig. This answer has 2 sig figs. This answer is better because, you have less risk of losing, but you wouldn't gain as much. There's a tighter range here. And so this would be better because the range would be between 1.095 to 1.104 pounds of gold. And so what we want to do here, is let's take a look at the All right, so here we have it. 1 kilogram is equal to 2.20462262. Would you say that this is exact? So 1 kilogram is defined as 2.20462262 pounds. Would you say that's exact? No, it's not exact. It's like pi. Is pi exactly 3.14? No, there's like thousands and thousands of digits. I think somebody actually measured something like, I forgot how many digits, a huge number of digits of pi. Do you really need all those digits? Well, it depends. It all depends on what you're doing. Sometimes yes, sometimes no. Do we need all these digits? No. Typically people just memorize it, 2.2 pounds per kilogram. And that's usually good enough because usually people are thinking about body weight, I weigh this many pounds, how many kilograms is that? That's usually what people are talking. But it depends on the calculation, depends on the scenario, because sometimes we need to be more exacting. We need to be more exacting, we need to use more sig figs here. And so for example, if I just stopped at 2.20, would you be happy? No, you wouldn't be happy because you're losing out on a little bit of gold. I mean, if it's a pound, you're actually losing out on quite a bit because it's so expensive. And so we can continue on. If this is exact, then that's an infinite number of sig figs. And so if we, continue on down here, 0.5, it would be 0.5. We could use this to help us. We could use this one. We could use this one, or we could use this one. 2.20. Now, if we round that number to 5 sig figs, what does it come out to? Or 4 sig figs, sorry. If we round that to 4 sig figs, what does it come out to? 2.205. We round that. So this would be 2.205 pounds per kilogram. And so now when we do that, what do we get? And so this one I'm going to use a calculator for, actually. Maybe I don't need the calculator for this. I should be able to do that in my head. But we can do it. 0.5 times 2.205. And this gives us 1.1025 pounds. Now this is what we have is 4 sig figs here. But if you take a look at my answer has how many sig figs? 5. I'm not allowed 5 sig figs because all of a sudden I'm going from a wider range to a narrower range. Well, how can I do that? I can't do that, from the numbers I'm using. I have to keep the range consistent. So this is 5 sig figs, which I'm not allowed. So what I have to do is I have to round this to 4 sig figs. But rounding this to 4 sig figs, this is going to come out to 1.0103 pounds. Okay, now if I'm selling you the gold, I'm going to lose out a little bit. You're going to be the beneficiary of this, right? And so it depends on how you convert it, because here, if you just use 2.20 pounds per kilogram, you would have come out with 1.10 pounds of gold, and I would have weighed out 1.10 pounds, right? But if we used instead of 2.205 pounds per kilogram, then you would have gotten an extra 0.003 pounds. 0.003 pounds, is that significant? Well, how many ounces are in a pound? 16 ounces. So let's go with 0.003 pounds times 16 ounces in a pound. That's 0.048 ounces. Do you know the price of gold right now? What is it? 15, 1800?
Oh, no.
Okay. Let's see what this is. Here it is.
Oh, wow.
1331.70. 1331.70. Yeah, $63.92. So about $64. You know, that you would have lost $64 if we sold it like this versus that. $64. I don't know. It's big. I mean, gold. A pound of gold's a lot of money. But anyway, what I'm getting at is this. What I'm getting at is we worry about sig figs. We worry about rounding. You know, rounding leads to errors. The errors might be beneficial. The errors might not. But in general, we don't. We want to try to minimize those errors. And so here, certain things we don't have a choice. You know, something like this is we're given. Something like this in the middle, we have a choice. You have a choice. And so here, I can't change this. It's either one sig fig or exact. I'm calling it in exactly. In exactly 0.5 kilograms, there's approximately 1 pound. Or in exactly 1.5 kilograms, there's approximately 1.1 pounds, etc. And so, you know, how precise do you want to get? You know, this is more qualitative, and this is becoming more and more quantitative as we go along. This is about 2 pounds per kilogram. And so it depends. Now, when we have a choice, this is what we do. When we have a choice, it depends on how exacting the givens are. You know, if everything's rough and qualitative, then you can be rough and qualitative with these. So, you know, if you're just talking about roughly, you know, 500 pounds, you know, roughly how many kilograms, then you can be very qualitative. But if we're becoming more and more exacting, more and more precise, then you have to be more and more precise with all these numbers. And so we have a simple rule for this here. You know, this is something that is tricky because here we have rounding. Let me talk a little bit about rounding. Each time we round something, we introduce error. So for example, if we round this, you know, here, if we round this from 2.205 and we want to round it to 3 sig figs rather than 4 sig figs, what would we round it to? 2.21. So if I had 2.205 and I round it to 3, it should go to 2.21, but it went to 2.20. Why is that? Why that is because in all calculations that we do, this is a calculation here, and all we're only allowed one rounding step. And so what that means is this. It means we don't want to do a domino of rounding. So for example, if I need to round this to 3 sig figs, I don't start over here and say, okay, we drop the 2, this stays as a 6. We drop the 6, I round that up to 3. We drop the 3, that stays as a 2. I drop the 2, well, that stays 6. If I drop the 6, this rounds to 5. If I drop the 5, this rounds to 1. That's a domino of rounding. Each time you round, you introduce error. And the error is called round-off error, and that leads to uncertainty in our answer. And so in science, we're only allowed one rounding step. So for example, if I want to represent this as 3 sig figs, I need to drop the 4. If I drop the 4, we're good at 2.20. Because if it's 4 and below, we leave it. If it's 5 and above, we round up. And so that would be 2.20. And so this would be a fact, because I'd never take this number to round it here. I'd take that number to round it here. And so we avoid rounding. And so only one rounding. One rounding step per calculation. Is allowed. And so if this is to 4 sig figs, how would I write that to 5 sig figs? What would it be to 5 sig figs? It would be 2.2046. Actually, that would be it. 2.2046 pounds per kilogram. So this is something I always think about. If you're like shipping a package or something like that, I was always curious what UPS uses. UPS uses this. They use 4 sig figs in their calculation when they're doing kilogram to pound conversions. They could go more, but that's what they use. So we're going to look at some numbers here, and then we're going to try to understand, are they definitions? That is, are they exact numbers, or are they... log out of this. So we'll look at a chemistry book here. We're going to look at some numbers. At the beginning or the end of the book, there's usually this. This is a periodic table here. And let's go on. Here are the elements in alphabetical order, and their symbols, names in alphabetical order. Here's a blank page. Here's another blank page. Here's something. Some of these are more geared towards physics. So, for example, acceleration due to gravity. This is the gravitational constant. Gravitational constant, do you think it's exact? The gravitational constant is exactly 9.80665 meters. No, this is measured value. In fact, there are more digits here. There are a lot of digits. So what most people do, when I was taking physics, do you know how many sig figs I memorized this to? To 2. It's 9.8 meters per second squared. The speed of light. You know how many sig figs, when I was a student taking physics, that I memorized it to? I memorized it to 1. 3 times 10 to the 8 meters per second. That's not good enough. 1 sig fig is bad because it's usually a lot of round off error. We don't like 1 sig fig because it could really hurt you or benefit you, but either way it's not good because it introduces a lot of uncertainty. And so 1 sig fig is usually bad. So in chemistry, I measured, and in higher level physics, you're going to use it to 4 sig figs, like 2.998. So, after I took in basic physics, I learned 3, but in higher level physics, it's 2.998, 4 sig figs. Means less uncertainty. Okay. Well, G and C, you don't memorize. In fact, I don't think we're going to use G and C at all in this course. Gravitational constant, speed of light. Although I did talk about speed of light, c, mc squared. Remember that? Mc squared. We're talking about conservation of mass and energy. But this is the c part of mc squared. R, we are going to measure that. In fact, we're going to, not measure, but we're going to memorize this. This is also measured. This is not an exact number. And this is measured, this is to, how many sig figs is this? 7 sig figs. How How, would this 0 here be significant? How about this second 0 here? Is that significant? It turns out that this second 0 is not significant either. Because if we convert that to scientific notation, let's convert that to scientific notation. Would I call it 0.20573 times 10 to the... So I'm making this number bigger. If I make this number bigger, then the exponent has to be smaller. So I move the decimal 2. So times 10 to the minus 2. Is this 0 necessary? No. So that 0 is not significant. It's just 8.2, not 0.8.2. And therefore, these are called placeholders. Any zeros, this is a rule of sig figs, any zeros preceding the first non-zero are all insignificant. It doesn't matter how many you have. You could have a lot. So for example, I might be looking at this, 0.000005 kilograms. This is not a super precise number. It's just these zeros are placeholders so that I write it in scientific notation. I got to move it 1, 2, 3, 4, 5, 6. I got to move it 6 over. So if I make this number bigger, so I'm going from a very small number to 5, which is a big number, then I make this smaller, times 10 to the minus 6 kilograms. That would be it. So anyway, all those zeros are insignificant, so this goes back to one significant figure, or it might be infinite. It depends how we define this number. Is it a measured value, or is it by definition? You know, what I'm talking about here. Well, Caracolici wants you to memorize this to 3 sig figs. So convert that into 3 sig figs. You know, measuring all 6 sig figs here. This is 6 sig figs, by the way. It's a hassle, and there are more. We can go to 7, 8, 9, 10 sig figs if you want. But for most calculations, do we need that level of precision? Like, for example, if something's very rough and there's a lot of uncertainty, does it really make sense to have a super precise? No. Because your final answer is going to be really rough, you know, and qualitative in that sense, or more qualitative. And so here, if you were to round this to 3 sig figs, what would it round to? Uh-huh. 0.0820? 0.0820 means we're dropping, we don't care about the 7, we don't care about the 2, we're dropping the 5. So if you drop a 5, you round up or you leave it? Yeah, you round up. So if we drop a 5 and above, we've got to round up. So this is going to be 0.0821. And so Caracolici wants you to memorize 0.0821. But in Chem 1A and Chem 1B, that's not good enough. 3 sig figs is not good enough. We need at least 4 sig figs. And so this is what I'd like you to do. We haven't hit that chapter yet. In fact, we're going to hit that chapter, chapter 4. But I'd like you to memorize it to 4 sig figs, because otherwise what you'd have to do is you memorize it to 3 sig figs, and then you have to erase it from your memory and re-memorize it to 4 sig figs when you hit Chem 1A. So we might as well memorize it to 4 sig figs. That way we just always have it. And so the 4 sig figs, what would this be?
Would it be easier if we just remember the scientific notation of it?
No. It'd be easier just to memorize it as 0.08. 0.08 is much easier, because when you do scientific notation, these numbers start to become less and less meaningful, like 10 to the minus 6, 10 to the minus 20. It just doesn't really register. But something like 0.08 does. You know, it's going to be 0.0820. 6. And so if you're going to memorize this, memorize it to 0.08206. Or this number turns out to be extremely useful. Extremely useful. There are different units or dimensions for R. So for example, if you have 12 eggs, you don't have to call it 12 eggs. You can also call it 1 dozen eggs. And the same thing here. If we have this as our R, then rather than using dimensions or units of atmosphere, we can use dimensions of bar. A bar and atmosphere are very similar. So the numbers are close. This is 82, this is 83. And so the numbers are similar, but they're slightly different. A bar is what the Europeans use. We use atmosphere. But otherwise, all the other dimensions are the same. Or it turns out a liter atmosphere is the same thing as what we call a joule. So this is a joule. And so typically we just memorize one, and then we can figure out the others if we know some conversions.
I thought bar was the new standard. ATM was the older one.
That's true. Bar is the new standard. So pretty much, bar is like the metric system, you know. ATM is like ours. And so the situation is that one time there's a big push to switch the U.S. to the metric system, but it failed. And so now there's a push right now to switch to bar, but I'm not so optimistic it's going to be successful. And so it might fail again. And so yeah, but you know, bar and atmosphere are so close to one another that it's not that different. This is a piece of an atom. Atoms are actually made up of three smaller particles called protons, neutrons, electrons. So this is what we call the charge on the electron. This is not an exact number here. This is the mass of an electron. Electron is just a piece of atom. This is H. All these are measured, and so there are more digits here. They just don't want to show all of them. So we probably aren't going to need them. Unless you're doing super precise work. If you're doing super precise work, then you need super precise numbers, and then you might actually need more digits. So for example, you know, like I said, you measure this, or remember this to 4 sig figs, but sometimes you're doing very precise work. You probably don't want to use 4 sig figs, you probably want to use more. So we use more here for this, depending on how precise you want to get. Well, these are more. Talk about later. Do you think this is exact? 1 meter is exactly 39.37007874 inches. Do you think that's exact? No, that's not exact. There are more digits here. Do we want to know them? Probably not. And so we, in fact, this first one, I just know to 2 sig figs, this first one. I just know that 1 meter is approximately 39 inches. That's it. But other than that, no. In fact, I don't even bother with that one. The one I know is that 760 millimeters or 76 centimeters is approximately 29 inches. Have you ever heard of this? Have you ever heard the pressure? You know, if you watch the weather, they're talking about how many inches of mercury, which is about 29 inches, which is about 76 centimeters of mercury. And so that's the only reason I know that. But this first one I don't even bother with. I know this one here. I know this one because this is a very important one to memorize. And so when I look at this one, what does it say? 1 inch is equal to 2.54 centimeters. So you think this is 3 sig figs here. But it turns out there's no uncertainty in this. Exactly 1 inch is exactly 2.54 centimeters. Whereas this one is exactly 1 meter is approximately 39.37 ... inches. And so this one is what we call a definition. 2.54 centimeters is defined as 1 inch. And therefore, do you see that? What does that say? It says exact. That means that, how many sig figs is this? It's not 3, it's, how many sig figs? 2. That's not 2. It's not 1. It's not 0. It's infinite. It's infinite because they didn't write it because there's going to be an infinite number of zeros after the 4. And so 1 inch, exactly 1 inch, which is infinite, is exactly 2.54. So there's going to be an infinite number of zeros. And so there's no uncertainty there. If you're looking at the precision range is essentially plus or minus 0. That's so small. And so, in other words, we call this 1 inch is exactly 2.54 centimeters. One way of doing that is some people do this. They'll draw a triple line like that. Triple line is just by definition. And so this is exact. Whereas, how about this one? 1 pound is equivalent to 453.59237 grams. Is that exact? No. And so what we say is this. We'd say in exactly 1 pound, there's approximately 453.59237 grams. A lot of people memorize this to 3 sig figs. So in 1 pound, there's 454 grams. Or 4 sig figs. In 1 pound, there's 453.6 grams. Either of those work. But which one should we memorize? Well, for sure, you should memorize this one. This one is the same. This one, you don't have to memorize. This one. So you should memorize this. And we need to memorize some others. So for example, let's take a look at this one. 1 liter is equivalent to 1,000 milliliters. Is that exact or approximate? This is exact. And 1,000 milliliters is equal to 1,000 cubic centimeters. Is that exact or approximate? This is exact. It says exact. So those types of things we need to memorize because those are exact. Whereas this one, 1 liter is equivalent to 1.056688 quarts. Is that exact? No, that's not. So I don't bother memorizing. This type of stuff will be given. You could look it up. And so, what types of things do we need to memorize? Well, we need to memorize certain ones like this: liters to milliliters. A liter to milliliter is what we call a metric conversion or metric prefix conversion. And so there are certain metric prefixes that we need to know the definitions of. And so, for example, a milli, like a milliliter or a millimeter, a milli, that prefix is defined as 10 to the minus 3, or 1/1000 is a milli. That's the prefix. We have others, lots of others. So if we go smaller, like 10 to the minus 6, do you know what we call that?
No,
Close. We call it micro. 10 to the minus 9, you'd be right. That would be called a nano. 10 to the minus 12. No, not femto. 10 to the minus 15 is femto. Well, I'm not going to talk about femto.
Pico.
Pico. Pico is really important because pico is about the size of an atom. An atom is about 100 picometers to several hundred picometers diameter. Right? And so picometer is important. And so this is one way of describing things. So for example, if you have a dollar bill, do you know about how much a dollar bill weighs? Do you think a dollar bill weighs exactly 1 gram? No, it was approximately 1 gram. So a dollar bill is approximately 1 gram. If you take that dollar bill and cut it into 1,000 equal sized pieces, do you know how much each piece would weigh?
1 milligram.
1 milligram. And so if you take that dollar bill and divide it into 1,000 pieces, that would be 1/1000th of a dollar bill, or 10 to the minus 3 is 1/1000. 1/1000th of a dollar bill would be a milligram. If you take that dollar bill and cut it up into 1 million pieces, each piece would weigh a microgram. You know, 1/1,000,000th or 10 to the minus 6 is a microgram. If you take that dollar bill and cut it up into a billion pieces, we would have each piece weighing a nanogram. Or if you cut it into a trillion pieces, each piece would weigh a picogram. And so how big is an atom? Well, let's take a meter. And if we take a meter, we'd have to cut it into how many pieces? Equal sized pieces. A meter, or we'd have to write how many lines across to get a picometer. Yeah, if we want a pico, you know, it'd be 1 trillion. So what we'd have to do is we'll have to divide a meter into a trillion pieces. Each piece would be a picometer. And then we take 100 of those picometers, and that's about the diameter of a what atom? 100 picometers is roughly the diameter of a hydrogen atom. You know, helium atom is about 60 plus picometers in diameter. And so that's pretty small. I mean, if you can try to visualize this in a trillion, then that's, you know, I don't know. Could you even see a trillion lines? No. If you were to count, could you count a trillion lines? 1, 2, 3, 4. How long would that take? It'd take a long time to mark. So anyway, that would be it. We wouldn't even be able to see it. We could go the opposite, so we'll go down to pico, but we can go up. Actually, there's one that's an odd one, and that is times 10 to the minus 2, or 1/100th. It would be centi. And then we're going to go big. And so here's our base. And we're going to go times 10 to the third. 10 to the third is 1,000. To be kilo. And then times 10 to the sixth would be mega. And times 10 to the ninth would be giga. And then times 10 to the 12th would be tera. So it used to be hard drives with kilobytes. Then everybody got excited when they got the megabyte hard drives, like a 5 megabyte hard drive. So that's quite a lot of data storage there. You know, 20 megabyte hard drives. I remember buying a 20 megabyte hard drive. It was pretty expensive. But now that's nothing. 20 megabytes, you can't store anything. I remember like dial-up modems, you know, over phone lines. 900. I had a 960 kilobaud modem. You know, kilobits per 960 kilobits per second was pretty screaming fast, you know, at the time. It's kind of expensive, but now it's nothing. Okay. Terabyte hard drives, yeah, cheap. So that's great, you know, data storage, stuff like that. But we have to memorize these things, and so let's. All right, so let's do one more. Here. So an example of this. There are different ways we can do these calculations. We can do them like if you go 0.5 kilograms, you know, and we go, okay, how many, what should we say? Let's go, how many pounds? Did I already do that? I already did that. How about if I do how many ounces? Did we already do ounces? I guess we kind of did it. Okay, then let's go, how many micrograms is that? Can we do that? Okay, so if, the way I approach a problem like this is by using dimensional analysis. So I would go 0.5 kilograms here. And then what I do is I try to look for a ratio that relates kilograms to something else. And so the ratio is going to be like this. A kilogram is 1,000 grams. And so 1 kilogram is 1 times 10 to the third. Well, 1 times 10 to the third, 10 to the third is kilo. And then we have our gram. And so there are different ways of representing this here. You know, I could say 1,000 grams per kilogram, that's easy, which is equivalent to, okay, a gram would be 1/1000 of a kilogram, so that would be 10 to the minus 3 here, kilograms. Is that right? Yeah. And so in other words, 1 gram would be 0.001 kilograms. And so all these are called conversion factors, and we have a choice when it comes to these things. A conversion factor is just a ratio that relates different things here. And we want a ratio like this so that we can cancel out the dimensions kilogram and leave us with grams. And then we go on here, the other one. And so we need some kind of thing that gets rid of grams. I might not have a strategy in mind, you know. Oftentimes chemistry problem solving is just, you know, you're trying to pick a path through the woods or through a jungle. You don't know which path to take, so you just keep taking paths until you get to your desired destination. And so I have no idea where I'm going. I'm just going to try to take paths. So grams will cancel out grams, but I need to relate grams to something else. Well, I can relate grams to micrograms. And so, okay, so if I have 1 microgram, a micro is 10 to the minus 6. And so I'm going to replace micro by 1 times 10 to the minus 6. I put the 1 there because my calculator is going to require the 1 to be there. And so I do that. Or, you know, there are other ways of writing this. I could write it like 1 million, you know, micrograms in 1 gram, which is equivalent to 1 times 10 to the positive 6 micrograms in a gram, etc. And so all these ones are going to give me the same answer. But essentially what dimensional analysis is, I'm going to get the desired unit, micrograms, and then I just punch it in the calculator. When I punch it in the calculator, I need that, you know. It depends on what kind of calculator you have. This is my calculator. I have the Casio FX115, so I have this key for scientific notation. This is a times 10 to the x key. And so I need a coefficient like 1 times 10 to the x. I just can't do times 10 to the x. So I'll put the 1 there. Other calculators will have this kind of key, and so they'll have the EXP key. This calculator has the EXP key. And so when I do the numbers, I'll do 0.5, okay, and then times 1 times 10 to the third, so 1 EXP3, divided by 1 times 10 to the minus 6, so 1 EXP. In some calculators, you have to put the negative first. Other calculators, you put the number first and then the negative. This one, we do the negative first. And so I have 0.5 times 1 times 10 to the third divided by 1 times 10 to the minus 6. That's what the E stands for here. And then equals. And so I end up with 500 million. 500 million micrograms. Now, it depends on how many sig figs I start off with. And so this is either going to be exact or 1 sig fig. So if this were exact, how many sig figs is this? Infinite. There are exactly 1,000 grams in a kilogram. Exactly. So this is infinite. How many sig figs are there here? Infinite. As well. There's exactly 10 to the minus 6 grams in a microgram, or there's exactly 1 million micrograms in a gram. No more, no less. This is exact. So if I'm starting off defining this as exact, then this is the way I'd read it. In exactly 0.5 kilograms, there's exactly 500 million micrograms. Or if this were 1 sig fig, and I'm starting this off with 1 sig fig, that means in 0.5 kilograms, there's approximately 500 micrograms, plus or minus, anywhere from, this would be anywhere from 460 million. If this were 1 sig fig, this would be anywhere from 460 million to 504 million, because those would round to 500 million. Do you see what I mean by sig figs? Okay. All right, let's stop. We're going to take a break.
So right there in scientific notation would be 5.00 times 10 to the 8 or something like that?
In scientific notation would be 5 times 10 to the 3, 6, 7, 8 times 10 to the 8. You're right, but it depends on how you want to do it. If you're saying exact, then it would be exactly 5. If you're doing it to 1 sig fig, this could be 1 sig fig or infinite sig figs. It's a little bit ambiguous because these are, sig fig rules. There's a little bit of, it's not so rigorous to define, and there's a little bit of uncertainty. Depends on how you say it.
So if we write 5.00, would that be incorrect?
That would be incorrect. If you wrote it as 5.00, then you're calling it 3 sig figs.
Well, I mean 5.00 times 10 to the 8.
Times 10 to the 8 is still 3 sig figs. And so if you were to write it 5.00, then that could be anywhere from 5.004 up to 5.0005. Sorry. Oh no. I'm on the high side here, 4.995. So I went from high to low. So it can be in this range here. Do you see? And that range is pretty narrow compared to, what is the range in here? If it's exact, it's right on. No more, no less. If it's 1 sig fig, it's anywhere from 4.5 to 5.4. That's a huge range. It's like a 50% range, right? Or not 50%, but it's a huge range. This is a very narrow range. And so this range does not match the range that's given. These are exact, so we have no uncertainty in these. And so the whole idea behind sig fig and sig fig rules is so that our final answer, which is the calculated value, has a similar kind of range of uncertainty as what we're given. If what we're given has no uncertainty, then we want our final answer to have no uncertainty. If what we're given has a big range of uncertainty, then our final answer is going to have a big range of uncertainty. And so it's just to keep track of the uncertainty in calculation. All right, we'll take a break. Does that answer your question?
Yes, sir.
Let's take a break for 10 minutes or so, and then we'll start again.